Example 3, we want to prove by mathematical induction that 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus ... all the way to n squared over 2n minus 1 times 2n plus 1 is equals to n times n plus 1 over 2 brackets 2n plus 1. So the first thing that we're going to do here is test that this proposition is true for some value of n. So let's say we test n is equals to 1. Okay, so if we test n is equals to 1, we should be able to see that left-hand side is going to be equals to, now if I take n is equals to 1 and substitute it into the general term, we're going to get 1 squared over 2 minus 1 times 2 plus 1, and that's just going to be 1 squared over 1 times 3. So therefore, when I'm testing n is equals to 1, left-hand side only consists of one term, and that's 1 squared over 1 times 3. So left-hand side in this case is going to be 1 squared over 1 times 3, which is equals to a third. And if I test right-hand side, we've got 1 times 1 plus 1 divided by 2 times 2 plus 1. So what this tells us is that we've got 2 divided by 2 times 3. The 2 and the 2 cancels, so right-hand side is therefore just equals to 1 over 3. And what this shows is that left-hand side is equals to right-hand side, which means that therefore the proposition is true for n is equals to 1. So that's the first step out of the way. Now the next thing that we're going to do here is we're going to assume that the proposition is true for n is equals to k. Okay, so assume true for n is equals to k. Now if we assume true for n is equals to k, what we're assuming is that 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus ... all the way to k squared over 2k minus 1 times 2k plus 1 is equals to k times k plus 1 over 2 brackets 2k plus 1. So we're assuming that this statement is true. Okay, so that's going to be our assumption. And what we need to do next is prove that this proposition is going to be true for n is equals to k plus 1. So if I start a new slide, okay, take note that the proposition we want to prove is 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus ... all the way to n squared over 2n minus 1 times 2n plus 1. And this is equals to n times n plus 1 over 2 times 2n plus 1. So what we need to do now is we need to prove that this proposition holds, okay, for n is equals to k plus 1. In other words, our RTP is 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus ... all the way to k plus 1 squared over 2 lots of k plus 1, that's going to be 2k plus 2 minus 1, so that's going to be 2k plus 1 times 2 lots of k plus 1 plus 1, so that's going to be 2k plus 3. Okay, so we want to show that this sum is going to be equals to k plus 1 times k plus 2 divided by 2 lots of k plus 1, which is 2k plus 2, plus 1, which is 2k plus 3. Okay, so that's what we need to prove in order to show that this proposition is true for n is equals to k plus 1. So if we were to start off with left-hand side, okay, so left-hand side is equals to 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus ... plus the last term is given by k plus 1 squared over 2k plus 1 times 2k plus 3. But before I write down the last term, let us consider what comes up just before the last term. So the term that comes up before the k plus 1 squared over 2k plus 1, 2k plus 3, according to the pattern, okay, we can see that the numerators are increasing by 1 at a time. So the term that comes up before the k plus 1 squared should therefore be k squared over, and then the denominator, I've got 1 times 3, 3 times 5, so they're essentially consecutive odd numbers. So the denominator of the second last term should therefore end with a 2k plus 1, and we know that we need to multiply this with a previous odd integer, and that is going to be 2k minus 1. Okay, and then we're going to plus the last term, which is going to be the k plus 1 squared over 2k plus 1 times 2k plus 3. Now, the reason that I chose to consider the second last term here is because 1 squared over 1 times 3 plus 2 squared over 3 times 5 plus dot 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 all the way to k squared over 2k minus 1 times 2k plus 1, this whole part here is essentially just our assumption. And we said that this summation is equals to k times k plus 1 over 2 brackets 2k plus 1. So if I substitute my assumption in, this is now going to be equals to k brackets k plus 1 over 2 lots of 2k plus 1 plus the last term that we've got over here, which is k plus 1 all squared over 2k plus 1 times 2k plus 3. Now, in order to add these two fractions together, the common denominator that we're going to use is 2 times 2k plus 1 times 2k plus 3. Okay, so if I check out this fraction, okay, let's say I draw a pretty big fraction bar that runs across. The common denominator is going to be 2 times 2k plus 1 times 2k plus 3. So in order to get to this common denominator, what I'll need to do is I'll need to take the first fraction here, and I'm going to multiply the top and bottom by 2k plus 3. Okay, so we've got a 2k plus 3. And then the second fraction here, I'm going to multiply the top and bottom by 2, right? So we can see that across the bottom of both fractions, we've got the denominator 2 times 2k plus 1 times 2k plus 3, okay? Which means that I can now essentially just add across the numerator. So in other words, we've got k, lots of k plus 1 times 2k plus 3 plus 2 lots of k plus 1 squared. And if we examine the numerator, right, we can see that both terms contain a k plus 1. So before we expand everything out, right, if we just factorize the k plus 1 out, what we have left is k plus 1 brackets k times 2k plus 3 plus 2 lots of k plus 1. And this is going to be all over, right? This is going to be all over 2 lots of 2k plus 1 times 2k plus 3. But keep in mind, right, that we need to turn this expression into our RTP. So our RTP is given by k plus 1 times k plus 2 over 2 lots of 2k plus 3. And of course, what we're going to do next is we're going to take a look at this bracket in the numerator, okay, the k times 2k plus 3 plus 2 lots of k plus 1. And what we want to do to this is, of course, expand it and factorize it to see what factors we have common in the top and bottom that allows us to simplify this fraction so that we are able to get to our RTP, which is k plus 1 times k plus 2 over 2 lots of 2k plus 3. So starting off with the left-hand side, or what we have of the left-hand side right now, okay, so starting a new slide, what we've got right now is left-hand side is equals to k plus 1 times k lots of 2k plus 3 plus 2 lots of k plus 1, right? And this is going to be all over 2 lots of 2k plus 1 times 2k plus 3. And of course, if we do our expansion, what we're going to get is k plus 1 outside of 2k squared plus k times 3, that's going to be 3k, plus 2k, that's going to be plus 5k, plus 2, all over 2 lots of 2k plus 1, lots of 2k plus 3. And 2k squared plus 5k plus 2 can be factorized, right, into 2k plus 1 times k plus 2 over 2 lots of 2k plus 1 times 2k plus 3. And here we can see that there's a factor of 2k plus 1 in the top and in the bottom. So we can therefore cancel these two out. And what we're left with is k plus 1 times k plus 2 all over 2 lots of 2k plus 3. Okay, and this is equals to our RTP. Okay, so this is equals to our RTP. So what this allows us to conclude is that therefore the proposition is true for n is equals to k plus 1 if it's true for n is equals to k. And from here we can now conclude, so therefore, since true for n is equals to 1, and true for n is equals to k plus 1. If true for n is equals to k, okay, the proposition is also true for n is equals to 2, n is equals to 3, n is equals to 4, dot, 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 and just keeps rolling itself forward, and all other positive integer values of n, okay, and all other integer values of n. Okay, so that's going to be our conclusion, right? So this concludes example 3.